Yes, so I wanted to talk about our little adventure into coupling a moving mesh to a fixed grid. This relates to our, shall we say, our work in, well, this is our work in coupling our nextSIM CIS model to the NEMO-Ocean model, nextSIM being a finite element model that runs on a moving mesh, and NEMO being a classical ocean model, which most of you should be aware of. I did most of the, or all of the essentially technical work, but I also like to thank, especially here, Laurent, Camille, and Claude, who helped us a lot on the NEMO side, without which Pierre and I would have been completely lost, I think. So, what I'll talk a bit about the sort of science motivation behind doing this rather quickly, and I will talk a bit about the problems that we face in coupling this moving mesh to a fixed grid. So what do we want from a CIS model? So what we want, the CIS modelers from a CIS model in particular, is to have something that describes the ice as a fracturing solid. That's how we think of the ice. The pack ice is a fracturing solid. And here we have some observations of the ice. On the left, we can see the observed deformation rates observed from satellite. And you can see very well these so-called linear kinematic features, where you have these extremely high deformation rates, extremely localized, in lines that go across almost the entire Arctic. So you can see up at the top is Russia, and left Alaska, and then we have Canada and Greenland at the bottom. And it's a very, very localized phenomena, these deformation rates. And this then relates to, on the right, the observed drift speed, which has very clear discontinuities in it. This leads, and then this links, in this case, the coupled ice-ocean model. We're interested in how this affects momentum transfer from the ice to the ocean, in the case of, let's say, discontinuous momentum or the discontinuous velocity field, and also to the ASC fluxes through these linear kinematic features, which essentially are ridges and leads in the end. So this should have a substantial effect on the coupling between ocean and ice. So to get this effect, we use our homemade nextSIM model, the model that's being developed at NERSC. I think I can safely say that nobody else can do it quite as well as we can. And to capture these localized features, we use different rheology from everybody else. We use Maxwell elastobrittle rheology, and we use a moving mesh as well. So it's a finite element discretization of a mesh, which is then adaptively remeshed as it moves. And why moving mesh? It's a localization question. That's the key point with why we want to move the mesh instead of attracting the field through it. And here we see, hopefully quite well, this is a video of the simulated concentration field, simulated by nextSIM. And you can see the mesh itself, you can see all the triangles. And here this is the Fram Strait, so it's Greenland on the left and Svalbard on the right. And you can see the ice flowing through, breaking up. And you can see that the mesh is following the solid pieces, the ones that are not broken. And then where the ice breaks, it's extremely localized. It is at the scale of the element. And there the mesh is deformed, triangles are stretched, and you have to recreate the mesh where it's highly deformed. While in the places where it's not deforming, we keep the old, the intact mesh. And this feature is, I think this is the best way to attract this kind of a field. it is really a discontinuous field, and it's not a fluid, it's a solid. So having a Lagrangian mesh makes a lot of physical sense. But it comes with a cost, and the cost in our case mostly, well, there's a numerical cost, and then there is a cost when you want to couple something. Coupling a moving mesh to a fixed grid is hard, or coupling a moving mesh to anything, in fact, is hard. And to tell you, so that you understand a bit the problem that we're facing, I'll tell you what happens actually when we remesh. So what happens is that, as you can see, the mesh itself is moving, and at some point, one or more triangles will be too deformed, and you have to recreate the mesh. Now, what we do, admittedly to make our life a bit easier, was that we gather all the fields to the root processor, and at the root, we generate a new mesh and a new domain decomposition, and then this is scattered afterwards to the compute nodes. Reason being that these kind of tools, the mesh generators and domain decomposition tools, they are not really capable of creating a new mesh on the separate compute nodes. Gathering everything to the root and doing things there and scattering again is tractable, is possible without a huge investment. But the problem is that the mesh, both the mesh and the domain decomposition, are dynamic in this case. So we would want essentially a coupler that not only recomputes the weight every time we remesh, but also computes the communication pathways. And there is no off-the-shelf solution for that, or at least it was not when we were starting this project, and I don't think there, well, things have been advancing in that direction, but I'm not sure if there is still. One thing that doesn't say on the slide, I should say, is that for a 10-kilometer resolution, which is sort of our reference, then we have a remeshing every three hours or so, give or take, during the model run. So remeshing is quite frequent, but it's not every time step. So what we did was something quite simplistic in the end, and that was to have a coupling exchange grid inside nextSIM. So with this setup, nextSIM essentially does all the heavy lifting, and the coupler is more of an. So the coupler in this case being Oasis. And what we do is that at each time step, each processor interpolates its fields onto a copy of this exchange grid, and each processor has a view of the global grid. And then when there's a coupling, all this information is gathered to the root, and the root gives the fields on this coupling grid to the coupler. So all that Oasis sees in this case is a single processor which is giving it or receiving from it coupling fields on a fixed grid. So there's a second problem actually for an ice-ocean coupled model, and that is that an ice and ocean are extremely tightly coupled, and we can't really suffer inaccurate interpolation between the mesh and the grid. So what we need is a conservative remapping between the mesh and the grid, and this has to be very fast and very efficient, because it needs to be done essentially. You need to recalculate the weights every time you do a remeshing. What we did in the end was to roll our own in this case. So we use weighted averages of overlapping areas of grid cells and triangles. The assumption behind this is that the fluxes that we are passing between the ice and the ocean, they are constant on the grid element, on the grid cell or on the element. And so we can therefore easily make the assumption that we can use weighted averages of overlapping areas. So this interpolation, we do it, so rather we calculate the weights during the remeshing step. So on the root, you gather everything to the root, you create a new mesh, and you calculate the weights. You scatter fields to the compute nodes, and you also scatter the weights to the compute nodes. And the compute nodes can then do the interpolation itself on their own domain. Now, this was in the end not very complicated, and we managed to do it quite efficiently because we had a lot of information about the mesh and about the mesh available already from the meshing tool. So we have a simple algorithm here, which the first step is to find the grid cell. Find the for each grid cell, we find the triangle which covers the P point or the center point. The video on the right is doing something funny, but I think you can see more or less what's happening there. So first we find the center point, and for that one, we know the triangle that we are in. When you're in that triangle, we do 3 checks. We check if one of the vertices are inside. We check for if one of the corners of the grid cell are inside the triangle, and we check for intersections between triangle and cell. And the nice thing here is that this is a recursive algorithm, so it can be done quite efficiently and relatively simple, in fact, in the end. And this is the first time I have a recursive algorithm in a CIS model, which I think that's definitely a first, but that was nice. So at the end of this, we know all the points. We know all the points of intersection between triangle and cell. We know all the vertices of the triangles, and we know all the corners of the grid cell, and so we can easily build the areas by connecting these and having it's a simple algorithm to calculate the area of the points. And yes, as I said, this was easy, or this is fast at least, because we know the connectivity. We always from the mesher we have an object. So this is all written in C++, I should say. So we have an object where we have connectivity between all the triangles. So when you're in a triangle, you know what vertices and sides there are, and you can find the neighboring one very quickly.
Einar,
and we also have
Einar, 2 more minutes. 2 more minutes.
Yes, thanks. And we have a quick tree search to find the triangle covering the P point. Mesh grid and land boundaries coincide, which makes things easy. And the assumption, of course, is that all the fields are constant on the cell and element. So as long as, so this makes this quite tractable and relatively easy to do. Yes, so I have one more slide, which is a bit about the future of this thing. I should say that this works now. We have a coupled nextSIM NEMO model which gives beautiful results for a regional setup in the Arctic and North Atlantic, 1/4 degree. But it is not very efficient numerically, and the main problem here is the remeshing algorithm. So gathering everything to the root and doing a remeshing there, that really slows us down and prevents us from scaling in any sensible way. So I think the future of the Lagrangian mesh, that hangs on the remeshing. What happens with the coupling? Coupling through the root is much less of a bottleneck still, but the road forward with the coupling depends a bit on which route we take with the remeshing. Meaning that if we're still with variable mesh and domain decomposition, then that puts a lot of demands on the coupler. But if we manage to have a static domain decomposition despite the mesh being movable, then that makes life much simpler for the coupler. And yes, that was all. Thank you.